Okay, so you're here for the deep dive.
That's right.
And that means, you want to cut through the noise.
Skip the summaries.
Exactly. Get straight to the real insights inside a whole lot of source material.
Consider it your shortcut?
To being genuinely well-informed. And today we're diving into something that's, well, it's completely reshaped our world.
Uh-huh. Deep learning. It started kind of quietly, then got very loud.
And our main source, it's The Deep Learning Revolution by Terry Sejnowski.
Yeah, Terry Sejnowski. And what makes this book special for our dive today?
He was there, right?
He was there in the labs, at the key conferences. He saw it. He shaped it from the very beginning.
So it's not just a history lesson, it's an insider's view.
Definitely. And our mission, really, for this deep dive.
Yeah, what are we trying to pull out?
It's about getting to the core, the essential stuff from Sejnowski. Where did deep learning actually come from? How did the basic ideas work?
And the breakthroughs, stuff we see now.
Right, the breakthroughs it's powered. And maybe most importantly, what does it all mean? Especially this connection between machine intelligence and, how our own brains work.
Okay, so we'll look at the roots. Neuroscience, early AI history. Some surprising stuff there, I guess.
Oh, yeah. And then unpack some of the key algorithms, the engines behind it all.
And connect it to today. The voice assistants you use, the online recommendations.
Self-driving cars, diagnosing diseases, even mastering games like Go. It's everywhere.
It really is. And Sejnowski stresses this mix of fields, doesn't he?
Totally. Math, computer science, neuroscience, psychology.
Yeah.
It's all woven together.
Which is its strength, but also
why it hit roadblocks. Faced a lot of skepticism. He even talks about a neural network winter.
A winter. Okay, that sounds intriguing. We'll get to that. But first, maybe just, take a second. Think about today.
Yeah.
Did you use a voice command? See a photo tagged automatically? Get an ad that felt weirdly specific?
Chances are yes.
Well, the revolution we're about to unpack is what's underneath all of that. So let's get into it. What does Sejnowski tell us?
Okay, so Sejnowski starts by painting a picture of early AI. For decades, the main game in town was symbolic AI.
Right, the idea you could build smart machines by, writing down rules.
Exactly. Explicitly coding human knowledge. Think if-then statements. Trying to build an expert system, say a doctor bot, by listing all the rules a doctor follows.
Or those early vision systems trying to see blocks by defining shapes.
Yeah, the classic Blocks world examples. But they hit a wall.
A big one, it sounds
A
like.
huge one. Turns out, writing down all of human common sense, all the unwritten rules we just know, it's incredibly hard. Maybe impossible.
And the real world isn't neat, logical rules. It's messy, ambiguous.
Precisely. So, meanwhile, you have this other group, smaller, kind of on the fringes.
The connectionists.
The connectionists, yeah, inspired by the brain. They thought intelligence wasn't about rules, but about networks of simple units, like artificial neurons.
Learning patterns from data.
Learning directly from data, from experience, like we do. Sejnowski was right in the middle of this group, often the underdogs.
And these underdogs hit a major problem early on, this winter you mentioned.
Great. Sejnowski points to a specific moment. Marvin Minsky and Seymour Papert published this book.
Minsky, a giant in AI at the time.
Huge figure, and their book mathematically proved that simple, single-layer networks, like the early perceptron from Rosenblatt,
They just couldn't solve certain basic problems.
didn't solve them. The classic example is the XLR problem. A single layer just can't learn it.
And that had a big impact.
A chilling effect, as Sejnowski puts it. Funding for neural nets dried up, interest just faded. People went back to symbolic AI.
Wow. So the winter sets in. But the connectionists didn't give up.
No, and this is key to Sejnowski's story. This core group persisted. They kept the ideas alive in smaller workshops, new conferences just starting up.
Like NIP.
Exactly. He points to the first Neural Information Processing Systems Conference, NIPS, in '87. That was a turning point. It brought this scattered community together. People who still believed learning from data was the way.
So even when it wasn't popular or funded, they kept going. What was driving them?
The brain. The fact that evolution already solved incredibly complex problems. Vision, hearing, language.
Using biological learning systems.
Right. So the thinking was, maybe we should try to mimic some of those biological principles for AI.
And neuroscience offered clues. Sejnowski's background is in both, right?
Yeah, crucially. He talks about how brains are amazing pattern recognizers. We learn by doing, by getting feedback. And intelligence doesn't seem to be stored in one place as rules. It's in the connections, the interactions of billions of neurons.
Okay, so they had the inspiration, the persistence. What were the key breakthroughs, algorithm-wise, that got them out of that winter? The perceptron had limits.
The big leap was the multi-layer network, putting hidden layers between the input and output.
Ah, so not just direct input to output.
Right. And that structure could solve complex problems like XOR. But the challenge was, how do you train it? How do you adjust all those connections in the middle layers?
This is where backpropagation comes in.
Bingo. Backpropagation. That was the revolutionary algorithm.
Okay, break that down a bit. Backprop.
So Sejnowski explains it as a really clever way to figure out the error, the mistake, in the network's final output.
Okay.
And then efficiently push that error signal backwards through the network layer by layer.
And adjust the connection as it goes.
Exactly. It tells each connection how much it contributed to the final error.
Yeah.
And tweaks its weight slightly. It's like assigning blame or credit iteratively.
So you feed it tons of data, it makes guesses, gets told how wrong it is, and backprop helps it adjust itself over and over.
That's the core idea. And the magic is, those hidden layers, they aren't programmed by a human. They learn to find useful features, patterns, abstractions in the data all by themselves.
Making the final decision easier.
Much easier. Sejnowski gives this great example from the 80s, Net Talk.
Yep.
Yeah, a network trained with backprop. They showed it written English text and fed it the correct sounds, the phones.
And it learned to read aloud.
I learned to read aloud just from examples. And apparently, it went through this phase that sounded like a baby babbling before it got good.
Wow. That's amazing.
It's a huge demonstration. Complex, rule-like behavior pronunciation emerging purely from learning statistics in data. No explicit grammar rules programmed in.
Which symbolic AI really struggled with, right? All the exceptions in language.
Exactly. Like go becomes went.
Yeah.
Neural nets just seem to handle that kind of stuff more naturally by seeing examples.
Okay, so that's supervised learning, where you have the right answers. But the book also talks about unsupervised learning. Finding patterns without being told what they are.
Right. And a really cool example Sejnowski discusses is independent component analysis, or ICA.
ICA. And the connection to the cocktail party problem.
Yeah, the classic problem. You're at a noisy party, lots of conversations. How do you tune into just one?
Or how does a microphone separate different voices talking at once?
Wow. Exactly. ICA is an algorithm designed to do that: find the original, statistically independent sources mixed together in a signal.
Okay, so a signal processing trick. But the connection to the brain.
This is the wild part. Sejnowski highlights what happened when researchers applied ICA not to sound, but to natural images. The independent components it found.
What did they look like?
They looked almost exactly like the simple cells that Hobel and Wiesel found in the visual cortex decades earlier. The cells that respond to edges and lines at specific angles.
Whoa. So an engineering algorithm rediscovered something fundamental about brain wiring.
It suggested that maybe the brain's early visual processing is essentially doing ICA, finding these efficient, independent features in the flood of visual input. A stunning example of that cross-disciplinary insight he champions.
Incredible. The book also mentions some other network types, like the Hopfield net and the Boltzmann machine. How do they fit in?
The Hopfield network was really important for thinking about memory. It's recurrent, meaning it has feedback loops. Information cycles around. And mathematically, it was shown to have stable states. These stable states could act like stored memories or patterns.
So you could retrieve a memory.
Yes. And crucially, it had content addressable memory. Give it a partial cue, like part of a pattern, and the network dynamics would settle into the complete stored pattern.
Just like seeing someone's face might trigger their name?
Exactly like that, a direct parallel. Then the Boltzmann machine. That was different again.
How so?
It brought in ideas from statistical physics, incorporating randomness, stochasticity, and its learning rule.
Yes.
It involved adjusting weights based on correlations between neuron activities, which basically mirrored Hebbian learning.
Neurons that fire together wire together, the famous neuroscience idea.
The very same. But the really mind-bending part was the learning process itself. It had two phases.
Two phases.
A wake phase, where it learned from the outside world, the data, and a sleep phase.
A sleep phase for a neural network.
Yeah. Where it wasn't looking at external data, but was internally generating patterns based on what it had already learned. Consolidating, maybe.
That sounds incredibly similar to biological sleep.
It was a powerful suggestion way back then that sleep might be computationally necessary for learning the deep structure of the world, not just memorizing examples. Boltzmann machines showed they could learn complex things like symmetry that simply nets couldn't.
So these early networks were already hinting at deep biological connections, memory retrieval, the role of sleep.
Absolutely. It really underscored the potential for learning complex patterns from data.
Okay, so we've got the history, the winter, these core algorithms, backprop, ICA, Hopfield nets, Boltzmann machines. How did this foundation lead to the applications changing everything today?
Well, a massive catalyst was the development or perhaps refinement and scaling of convolutional neural networks, ConvNets.
Convnets. These are huge for images, right?
Huge. They turned out to be incredibly good at processing grid-like data, like pixels in an image. And Sejnowski explains the architecture is directly inspired by the visual cortex.
How our brain processes vision.
You have a hierarchical structure. Simple cells see edges, later layers combine edges into textures or shapes, then parts of objects, then whole objects.
So convnets kind of mimic that hierarchy.
They do. They use these small filters that slide across the image, learning to spot features. Early layers learn simple stuff like lines. Deeper layers learn combinations, more complex things.
And Sejnowski was involved early.
Yeah, he mentions Yann LeCun's work in the 90s using ConvNets to read handwritten zip codes for the post office, a direct ancestor of today's image recognition.
And then things really took off in the 2010s. What changed?
Two big things. Massive amounts of data becoming available online and...
Computing power.
Exactly. Especially the use of GPUs, graphics processing units. They're designed for video games, but turned out to be perfect for the parallel calculations needed to train deep networks.
Suddenly, you could train much bigger networks on much more data.
And that led to the breakthrough moments, like AlexNet winning the ImageNet competition in 2012.
The big image recognition challenge.
Right. AlexNet, a deep convet, just blew away the competition. Its performance shocked everyone. That was really the moment deep learning went mainstream in AI research.
Okay, so convnets for perception. But the book also talks a lot about reinforcement learning. Games like backgammon, Go. That feels different.
It is different. Reinforcement learning isn't primarily about learning from a fixed data set. It's about learning by doing, trial and error.
Getting rewards or penalties.
Exactly. Interacting with an environment. Sejnowski recounts the TD Gammon story from the 90s.
TD Gammon?
A program that learned to play backgammon, and it reached world champion level.
How?
Purely by playing millions and millions of games against itself, using a technique called temporal difference learning to get better at predicting outcomes. No human games needed initially.
You self-play. And that scaled up to AlphaGo?
Massively scaled up. DeepMind's AlphaGo, beating Lee Sedol, the human Go champion, was a huge public moment.
I remember that.
But Sejnowski notes the really profound step was AlphaGo Zero.
Zero? Why zero?
Because it learned Go entirely from scratch. No human games, no opening strategies fed into it, just the rules and self-play.
And it got even better.
It crushed the previous versions of AlphaGo. And it developed totally new, creative, frankly alien strategies that humans hadn't thought of in millennia.
Wow.
For Sejnowski, this showed the power of pure learning from simulated experience, creating intelligence that could genuinely surpass human abilities in really complex areas. He also mentions DeepStack beating poker pros, handling uncertainty and bluffing.
It's kind of mind-boggling, creating superhuman skill just through self-simulation. And now these techniques are everywhere. Self-driving cars seem like the poster child.
For sure. Sejnowski reminds us of the early DARPA grand challenges, those robot car races in the desert back in the mid-2000s. Machine learning was already key then.
And now deep learning is driving the perception systems.
It's crucial. Letting the car see, identifying pedestrians, other cars, lanes, predicting what they'll do. That's deep learning, mostly convets working on sensor data.
Then there's language. Siri, Alexa, Google Assistant.
Ubiquitous now. And Sejnowski points out that deep learning breakthroughs were what finally got speech recognition accurate enough to be useful for everyday interaction.
Human-level performance, basically.
Pretty much. And that's changing how we interact with computers, moving beyond screens and keyboards.
Healthcare, too. The book mentions a lot there.
Yeah, things like analyzing medical scans, x-rays, MRIs for signs of disease, detecting sleep stages from EEG data, predicting patient risks. Finding subtle patterns in complex medical data is something deep learning is really good at.
Patterns a human doctor might miss.
Or patterns that are just too complex to define with simple rules. The potential Sejnowski sees for faster diagnosis, more personalized treatments. It's huge, though getting it integrated into practice has challenges.
And finance. Weren't they early adapters?
Especially for fraud detection. Sejnowski talks about companies like HNC using neural nets way back, even decades ago.
To catch fraudulent credit card use.
Yeah. The networks learned to spot subtle, suspicious patterns in transaction data, far better than the old rule-based systems, saved banks billions.
Because it's all about spotting patterns in massive data sets.
Exactly. A perfect task for these methods.
Even education gets a mention. Sejnowski's MOOC.
Right. Learning how to learn with Barbara Oakley. He's clearly proud of that. Using neuroscience insights to help people learn better. It connects back to the book's themes.
And the future vision there. Personalized tutors.
Digital tutors that adapt to you, your pace, your style, combining AI with what we know about how humans learn.
The book also touches on robots understanding us better. Social robotics, facial expressions.
Yeah, teaching machines to read emotional cues. It's super complex, but key for making AI interaction feel more natural, more intuitive.
Okay, so all these applications exploded, but you mentioned hardware earlier. That was also critical.
Absolutely critical. Sejnowski makes it clear. Part of that long winter was just not having enough computing horsepower.
CPUs weren't fast enough.
Not for training the big networks needed. The shift to GPUs, those graphics chips, that was a game changer. Their parallel processing power was just what deep learning needed.
And now we have even more specialized chips.
Right. Google's TPUs, tensor processing units, and even research into neuromorphic chips.
Neuromorphic, like mimicking the brain's hardware.
Trying to, mimic the structure, the low power consumption.
Hmm.
Sejnowski sees these hardware advances, whether digital or maybe even analog or spiking systems, as vital for the next wave of progress, because the brain is still way more efficient.
And he keeps coming back to the brain, doesn't he? Not just as inspiration, but...
As a partner in discovery, he calls it. He draws parallels constantly. Convex and the visual cortex, recurrent networks like LSTMs and working memory, reinforcement learning, and reward pathways involving the basal ganglia.
So neuroscience shows what's possible and gives hints about how.
Exactly. And big projects like the Brain Initiative, which Sejnowski is involved in, aim to map the brain in more detail. That knowledge could feed back into designing better AI.
It really feels like a virtuous cycle.
Yeah, this deep dive really highlights that. The ups and downs of research, the skepticism, the breakthroughs when ideas meet technology.
And that mix of disciplines being so important.
Crucial. But Sejnowski is also clear, this isn't like AI solved. Big challenges remain.
Like the black box problem.
That's a major one. We often build these incredibly powerful networks, but we don't always know why they make a particular decision.
Which is a problem if you're using it for, say, medical diagnosis or loan applications.
Exactly. Explainability is a huge area of research. And then there's common sense.
Ah, yes. AI still struggles with basic common sense.
Fundamentally. Sejnowski points out even a toddler has a rich, intuitive grasp of how the physical world works, how people interact. Stuff current AI just doesn't get.
How does he think we get there?
He suggests it might require something more like human development learning through interacting with the world, embodiment, maybe over a long time, not just training on static data sets.
Okay, so let's try to wrap up this journey through Sejnowski's deep learning revolution. We started way back, brain inspiration, the symbolic AI dominance.
Then the connectionist underdogs, the neural network winter after the Minsky critique, but the persistence.
Right, leading to foundational algorithms, backpropagation, enabling deep networks. ICA, finding features connecting to vision, Hopfield nets for memory, Boltzmann machines hinting at sleep's role.
Then the explosion driven by ComNets, GPUs, and big data. ImageNet.
And reinforcement learning's triumphs in games, TD Gammon, AlphaGo, AlphaGo Zero, showing superhuman skill from self-play.
Which led to applications transforming everything. Self-driving, speech recognition, healthcare, finance.
All based on this shift from programmed rules to learned patterns.
And throughout, this constant dialogue between AI research and trying to understand the brain.
But as you said, still facing big hurdles. Explainability, common sense.
Definitely. It's gone from the fringe to center stage, doing amazing things, but Sejnowski emphasizes it's still evolving fast. Inspired by the brain, yes, but not yet matching its full flexibility.
And that brings us perfectly to a final thought Sejnowski leaves us with, something for you, the listener, to chew on.
Yeah, he makes this really interesting point. Our brains are constantly learning, right? We adapt to new situations, we pick up new skills, while holding on to what we already know. We're always online, learning from the world.
He calls the brain a super Turing machine because of this constant adaptation.
Exactly. But most current deep learning systems, they get trained, often on a massive but static data set. Then they're deployed, basically frozen,
Yeah.
they don't typically keep learning from new experiences in the real world.
They learn once, then they just apply that learning.
Right. And the huge challenge, one of the next frontiers he points to, is building AI that can do that lifelong, continuous learning. Learning new things without catastrophically forgetting the old things, something our brains do remarkably well.
So the provocative question is, what does this fundamental difference, our fluid, continuous learning versus the often frozen state of current AI, tell us about intelligence itself? And what kind of breakthrough might unlock that truly adaptive, continuously learning AI?
A deep question indeed.
Something to think about as you see AI changing the world around you. Until the next deep dive.